Hello, everyone. Yet another awesome Shiny Developer series, as always. The next talk is very interesting. It's an intersection between healthcare, statistics, and software development. It's a great example to show that how Shiny is used in real world to make real impact. The topic for this session is standardizing acute kidney injury across different populations. And I'm happy to invite our next speaker, Ishan Sharan from Yale.
Hi.
Hi.
Thanks very much. Can you hear me all right?
Yep.
Okay, cool. Uh, I will go ahead and share the screen then.
Okay. Can you tell us a little bit about yourself?
Absolutely. So my name is Ishan Saran, and I am a researcher at the Yale School of Medicine. And let me go ahead and so I'm really excited. Thank you for the opportunity to be presenting some of my work. I think it's a great showcasing of Shiny and how it's, like you said, how it's being used in the nephrology space. So we're doing a ton of cool stuff, and I think Shiny's really bringing a lot of the conceptions to tools that we can use. So shall I begin?
Yeah, sure.
Cool. Let me go ahead and swap over here. Okay, can you, apologies. Can you see this?
Yeah, we see your slides.
Okay, awesome.
Could you
So,
maybe hide the small thing in the bottom?
yes. Uh, okay, how is that?
It's amazing. Yeah.
Okay, cool. So I'm really excited to showcase some of the work we've been doing to standardize the definitions for acute kidney injury. So without further ado, let's get started. The Mayo Clinic estimates there are over 200,000 cases of AKI in the US every year. That's a real problem because AKI has increasingly high healthcare costs, both in terms of lives and dollars. These are statistics published from Susan Titafong and colleagues at the St. Elizabeth's Medical Center in collaboration with the Tufts School of Medicine, showing that inpatient mortality was anywhere from 1 in 4 to 1 in 5 in adults and 1 in 10 in children. Moreover, if left undealt with, renal insufficiency can lead to hemodialysis, which has been shown in the literature to increase healthcare costs by as much as fourfold, jumping from $11,000 per hospitalization to $42,000. This accounts for the exceedingly high healthcare costs. Silver and Chertow at the University of Toronto estimate that that cost is anywhere from 5.4 to $24 billion. This is because AKI has a complex etiology. There's a growing shift in the field towards thinking about AKI as a multi-organ dysfunction rather than a single organ failure. What I have on the right here is a diagram showing the intersection of AKI with various other ailments. As you can see, AKI is associated with things such as cardiac surgery, drugs, sepsis, and cancer. It's for this reason AKI is a hard syndrome to pin down. Its incidence in literature has a wide reported variance, ranging anywhere from 4 to 17%, to 66% even. With more than 35 definitions in the literature, doctors are confused and scattered on how to treat the complication. That's the problem we're trying to address with the AKIFlagger. By implementing a set of standardized research definitions into a computer program, the research and scientific community at large will be able to benefit from the tool. What we did was start off with the standard KDIGO guidelines, from which we further derived 3 definitions: the rolling minimum window, the historical baseline trumping, and the baseline creatinine imputation definition. Here's how it works. The rolling window borrows a tool from statistics known as a sliding window to calculate the rolling minimum creatinine within the past 48 hours. Then it compares the current creatinine value to that minimum value, and if the KDIGO criterion are met, it flags the patient as having acute kidney injury. Historical baseline trumping takes advantage of prior knowledge of the patient's creatinine. If the patient's baseline creatinine can be ascertained, then the current creatinine value is compared to that patient's outpatient creatinine values from 365 to 7 days prior to admission. Values from 7 days prior to admission are discarded because hemodynamic fluctuations near admissions often cloud creatinine measurements. Finally, we have the baseline creatinine imputation definition. This definition borrows a method of imputation originally developed by Levi and colleagues in 2009 and updated by Inker et al. In 2021. The main idea is to back calculate an estimated serum creatinine if there are no outpatient creatinine values from 365 to 7 days prior to admission. The calculation assumes an estimated glomerular filtration rate, or EGFR, of 75. The updated equation takes the race variable out of the equation for estimating the GFR and is part of a growing movement to remove race from the analysis. So now I'll go through a demo of how someone would use the AKIFlagger. So let me swap over to the R console here. And so starting with an empty environment, once you've installed the package and everything, there's an app.r file which you would run. And let me make this nice and big. So the tool is currently still largely in dev mode, but the main idea is a user would select a file, a CSV file, from their computer. And the file would contain basic information about the patient ID, the creatinine measurement, the timestamp at which the creatinine measurement was taken, and then a column that's inpatient or outpatient, which tells whether or not the inpatient measurement was made in, or whether the creatinine measurement was made in an inpatient setting. So if I just do this is what the example data looks like. It's a patient ID, the creatinine measurement, the timestamp that measurement was taken, whether or not it was made in a hospitalized or an inpatient setting, and then some other common variables such as age, sex, and race and admission time. So that is the input data, just a sample of what a user might input. These are very common values that, say, a nephrologist or an internal medicine doc would have when they're sort of evaluating acute kidney injury. And you can see by default, the rolling mem window or the RMW definition is set. And the user could also select a padding value to put on top of, depending how long they'd want to select the time frame. And then they simply click compute AKI, and the data frame, right as the data frame is inputted, is outputted with this extra AKI column added in. And that's the AKI calculations done under the hood, and Shiny returns that as a CSV file which can be downloaded. If the user inputs multiple definitions or selects multiple definitions for AKI, they can compute AKI. And now, rather than returning a single AKI column, multiple columns will be added into the data frame of each definition, and a Venn diagram showing the overlap between the different patient population groups is plotted. And again, the data can be downloaded at ease. Let me go ahead and go back to the presentation and just really quickly show some results that we've derived on actual data. So this data, just as sort of primer, is a COVID data set, COVID positive patients, just the first encounters from where they're COVID positive patient, just the first encounters of the data set. And there are 40,106 patients. And so what you can do once you have the different definitions of AKI sort of added in is you can compare which patient populations are being captured by each definition. And so you can sort of see here that there's a large amount of overlap between each of the definitions in terms of which patient populations are being captured, but there's also a significant amount which, say, the HBT definition is capturing that the RMW is not. Another thing to note is that as you progress in AKI stage, you sort of see different patterns. So where HBT is sort of a nice subset of BCI in earlier stages, that's not necessarily the case as you move later on in stages. When you're looking at which patient population groups are being captured, you can also tie that to outcomes of interest that physicians or nephrologists might be interested in, namely how well are each of the definitions capturing, those patients or associated with patients who are going on to be dialyzed or death, or how does that compare to length of stay? And so this this is sort of one diagram that can show uh, that apologies. Um, so what you can do is you can create a confusion matrix where you use the definition of interest as your predictor, as your exposure, and then your ground truth is whether or not you observe a subsequent rise in creatinine. And all of this sort of analysis is being done based on creatinine trajectories. And so you can analyze sensitivities, specificities, and this is current work that we're doing, working on integrating these types of analyses into the AKIFlagger. But you can sort of select a time frame of interest. Here on the left, I believe I have sensitivities, and on the right, I have AUCs, area under the receiver operating curve, characteristic curve. And on the x-axis, there's sort of a percent increase in creatinine, and on the y-axis, there's an amount of time from admission. I know the axes are not labeled that well. That's because there's still a little bit of sort of decision making that's going on the research end as to how sort of the time windows we want to be using. But it generally ranges anywhere from 24 hours to 168 hours. So that's about anywhere from days to a week. And so sort of once the nephrologist has selected a window, the idea is that most physicians would agree, okay, kidney injury actually occurs somewhere in here, in this window. And so by selecting a region of interest, you can then go on to choose what might be the best definition based on whether you're trying to optimize across sensitivities or your AUC or whatever model selection technique you're using. So there's a lot of exciting work going on here. I should definitely give due credit, not just to myself who's presenting this, but also the other lab members, Doctors Ugo and Dr. Abinet. They're two research fellows. One is a clinical nephrology fellow. Another is a research fellow. Adi, the main machine learning artificial intelligence expert. I myself am the developer, and Dr. Perry Wilson, who's the principal investigator. So these are some of the references, and thanks very much for listening to my talk.
Hi. So we did have few questions. Like Maya wanted to know that how the Venn diagrams were created. Was that an R package? And looks like it was an R package. Can you talk a little bit about that?
Yeah, absolutely. So yes, the R package is Venn diagrams. So there's this sort of like the nuance between Euler diagrams versus Venn diagrams, which is just Venn diagrams are not area proportional, but Euler diagrams are area proportional. Sorry. And so it was done using an R package called Venn diagram, and happy to show you how that works. But it's basically taking each of the counts of the AKI definitions.
Okay. So your analysis required you to have area proportions accurately shown. So that's why you chose Venn diagram?
So that's where Euler diagrams would be a little bit better than Venn diagrams. It turns out it's a pretty hard problem in general for more than 3 groups. I'm just getting into minutia for no reason. It's an R package that does the job.
Okay.
Yes.
Yeah.
Thanks.
And let me check the comments. Yeah, everyone is super happy with your application. Can you share the GitHub code? Maybe I think some people will be
Yes.
interested in that.
Yes, absolutely. Let me go ahead and Let's see.
Okay. We have one more question. Are you planning to link this to hospital records with sensitive data, um, mandating a secure app for researchers or clinicians to upload data with anonymized IDs? That's an interesting question.
Yeah. So that is a great question. Um, and so let me think about it, because we are really sort of privy to PHI protected health information, making sure that none of that gets leaked. The plan is to fully open source the code in such a way that any nephrology researcher supposing that they could anonymize the data on their own, and wanted to maybe download the Flagger on their local machine, uh, they could use it, containing PHI. And then as for whether a researcher who had protected health information that wanted to use the tool, um, we're we're working on putting together the proper protocols in place so that you could, if you had some sort of an anonymous form, um, to detect the acute kidney injury, you could do that using the AKIFlagger. So rather than looking at like raw timestamps, it would be looking at time deltas, like how long after admission date is this. So we're working on that right now. That's exactly the way in which, like, the future directions for research. Yes. Quick question: where should I put the GitHub link, the portfolios?
You can just put in the private chat and we'll update it over there. No problem.
Okay,
Uh,
fantastic. Thank you.
okay.
Thanks for the question.
And yeah, we still have time, so we'll go with a few more questions.
Sure.
How did the idea for this app come into inception? Like, why Shiny?
Yeah. So let's see. So I only got into the nephrology space in 2019. So 3 years. But apparently this has been a big problem for maybe upwards of a decade. This lack of consensus definition for acute kidney injury. And so originally this started off as a package, as Python code, because I'm originally a Python programmer. So this was originally done as a Python package. It's fully available both in R, Python, and we're working on a standalone app right now. But it just so happened that Shiny's capabilities and their sort of infrastructure was one of the best to sort of take it from some raw code to a nice consolidated platform GUI that you could use, that because your average nephrology clinician researcher won't be as maybe privy, as well versed in R code as you or some of the developers who are watching this. So it started off as R, as a Python package, and then an R package, and then on CRAN, and it's slowly built into a nice platform.
Okay, awesome.
Yes.
Okay. Mm, okay, I see that you don't come from a software development background. You have your own academia. So how did you learn Shiny? Because I believe like it could be challenging for new people to start. So
Sure. Well, the great thing about R and R Shiny is how awesome the community is. So I start off with, is it Hadley Wickham's book, the r-packages.org, um, which is online. So I started off not with Shiny, but with R packages and figuring out how to develop the code. And there's some great resources online for creating Shiny apps. Mainly the Shiny galleries, going through the Shiny tutorials. They have written and video tutorials, which are awesome. The YouTubes that Absalon has are fantastic resources for some of the minutia. So r-packages.org by Hadley Wickham is how I learned much of the, because I come from a much different background, but a lot of the freely available resources online are pretty good. And then
That's
if anyone has any specific like questions, I'm happy to answer them afterwards. My email, I don't know if I put it in there. It's is439@yale.edu or ishansaran65@gmail.
okay.
Please feel free to reach out or anything.
Awesome. Uh, what were the key challenges you encountered while developing your application?
Uh, this is a good question. There are a lot of challenges.
Amen to that.
You sort of just smash your head against a wall until you bulldoze past them. There's sort of a flow, which is a document. You write the documentation, then you write the unit tests, then you um, reiterate many times. You work on functional logic a little bit, then a little bit of then a little bit of documentation, then a little bit of vignettes. Vignettes as more long form documentation. Sort of balancing all of the different components. Figuring out how to partition the time, how to appropriately budget time was maybe one of the big challenges while developing that, because there's so many components. Like as soon as you create the R package, there's like 15 different files which are created. There's a documentation file and a namespace, and you have to figure out what namespacing is. And so it's just slow and steady. A lot of different challenges will pop up, and then you Google a bunch. I wish I could say kidney injury was much different than regular dev, but it's dev work.
Okay. And I also remember that you used to have a Python script for doing these, and so what I believe you have some experience with Python a little bit at least. So what key differences do you see between R and Python?
Yeah. So I would say broadly, in what takes 8 lines of code in Python takes 1 line of code in R, but the 8 lines of code are a lot more logical in Python. In my personal experience, R just sort of requires a little bit more tinkering. Python is a little more chasing rabbit holes, like starting off maybe in Seaborn and then going to matplotlib documentation and just going through they're different. They're pretty similar fundamentally. It's a lot of ours just maybe a little more hacky, like a little more tinker. You have to do a little more to try to move things in place or get things exactly how you want it, whereas Python allows for a little more customizability. They're both excellent functional languages.
Okay. So have you used the package called Reticulate? Like it allows you to communicate between Python and R.
I've used a little bit of it. I try to get it working, but now I sort of try to where I am personally, like I'm trying to both up my Python and my R skills. So I try to code it once in Python and then in R, or once in R and then in Python. Double the effort, but twice the learning too, right?
Yeah. Earlier, but how long did it take to develop that shiny application of yours?
The bulk of the logic was done in about a 2-month period. But then the refining and the reiterating was maybe stretched out over 6 months or so, 4 to 6 months maybe.
Okay.
Um,
Awesome. Yeah. So do you have anything else to share with us?
Not that I can think of. Thank you so much for listening to me talk. Please check out my GitHub. Please reach out to me for any questions. Thank you so much for inviting me. Thank you for allowing me to do this.
Thanks a lot for a great session. It was awesome. Yeah. Bye.
Cheers.